All right, so as promised, this is 11.9, and there's only going to be 3 slides that you're going to get to cover, but you need to write down exactly what I write down, especially on the next slide. So the question is, how do we know what the electron configuration is of an element? How do we know where those electrons are and what orbitals they probably should be in? This next slide looks a little overwhelming. It's an old system. I'm going to show you a new system tomorrow, but I need you to go along with it. And this is how we figure out where electrons are located in an atom. So we're going to start with looking at this. I need you to draw the arrows where I draw them. Let me pick a different color. Let's try blue. And a little bit bigger of a line. So electrons in an atom, the first electrons are going to be found in the 1 energy sublevel. The shape is the S, and the maximum number of electrons is going to be 2. After there are more than 2 electrons that need to be taken care of or positioned for a different element, they will then go to the 2s orbital. This is the second principal energy level, and the next 2 electrons will go into an s shell as well, and that can fit a maximum of 2. Once those are filled and we have more electrons to account for, we then are going to go to the 2p level. So it's a second principal energy level. It's p orbitals. Remember that there were 3 different p orbitals, a pair of them on the x, a pair on the y, and a pair on the z axis. The total amount of electrons that can be held within a p orbital is 6. Once we fill up and use all those 6, so we have an element that has more than 6, 7, 8, 9, 10 electrons, we're going to go up to the 3rd principal energy level and put the next electron or 2 electrons in the s. If we have more electrons than 6, 7, 8, 9, 10, 11, 12, we're going to put them into a 3p orbital. And we can fit the next 6 in a 3p orbital. And this is going to continue. But instead of going from a 3s to a 3p to a 3d, it actually takes less energy for the electrons to pop out to a 4s orbital at this point than it does to fill a 3d. Because remember that the 2s surrounds the 1s, 3s surrounds the 2s, and so on, and it gets really, really crowded in there. So it's actually easier for the electrons to hop out to the 4s than it is to go to the 3d. So if we need to account for more than those 2 electrons, we then need to go back and we'll put electrons into the 3d orbital. From the 3d then, if we have more electrons, they're going to be found in the 4p. We'll fill that next. And again, just like it was before, we're going to hop down and we're going to fill the 5s instead of the 4d because of the energy required. It's easier for them to be out here. Go back up after that. We're going to fill in the 4d. From the 4d, we are going to go to the 5p. From the 5p to the 6s. From the 6s, and all we're doing is accounting for electrons. Back up to the 4f14. From 4f to 5d, 5d to 6p, 6p to 7s. 7s is going to go to the 5f and down to the 6d, and that's where we'll stop. So you just have to follow the arrows when looking at the electron configuration. So I'm going to do an example on this one, and put that in a different color. Put it in red. We are going to write down the electron configuration of hydrogen. And that's what I asked for, is to show me the electron configuration of hydrogen. Well, you look at the periodic table, and you notice that hydrogen has 1 proton and 1 electron. So all I have to do is account for 1 electron. So we're going to start up here at the top. So the electron configuration for hydrogen is 1s1. Now maximum could be 2, but we only need to put 1 in there. Let's choose another one. Lithium, for example. We look at lithium and it has 3 protons and it has 3 electrons. So we're going to put the electrons in 1s. We'll put 2 of them in there, and then the next ones will go into the 2s, but I'm only going to put 1 in there. So the number of electrons total when you get finished, when you add up the subscripts, should be equal to the number of electrons found in a neutral atom for that particular element. And you can flip to the next slide for yourself if you'd like to put some of these examples on. I'm going to stay on this page with the examples just because it's easier for me to stay here with this than to flip it back and forth. The inner writer pad doesn't like to keep what it has on here. So just want to give you that to go ahead and flip to the next page. Just keep this chart available. All right, let's pick a number or an element with a little bit higher number. Let's look at, for example, sodium. Sodium has an atomic mass of about 23, and it has an atomic number of 11. That means in a neutral atom, it has 11 protons and 11 electrons. So let's account for those 11 electrons. Where do we expect to find them? We'll start with a 1s2. That takes care of 2 electrons. We're going to go down to the 2s, and we need to put 2 more electrons in there. So there's 4 electrons total. Then we'll go across to the 2p. We can put up to 6 in here. So we're going to put 2p, and we need all 6 of them in there. There's 6, 7, 8, 9, 10, but I need 11. So where am I going to put the next one? It's going to go to 3s, and I'm only going to put 1 out there. So I've accounted for my number of total electrons. Another thing that I'm going to add in here now is an orbital diagram. And I combined the two just because I think they make sense to put them together. So remember Pauli's exclusion principle, and it says if we have 2 electrons in the same orbit, they're going to go opposite spins, opposite directions. So what we're going to do is below the sublevels, you're going to put, for example, this one is the S, and it can hold a total of 2 electrons, so 1 box. This is the S, 2 electrons, 1 box. That's how many orbitals. The P, though, has 3. Make sure you leave yourself room. And the S has 1 box. All right, so we have 2 electrons. So we're going to have an arrow up and an arrow down to represent 2 electrons in this orbital with opposite spin. The same thing for the S. Arrow up, there's 1. Arrow down is 2. For the 2p, we have a full house again. So we have arrow up, arrow down, arrow up, arrow down, arrow up, arrow down. And the 3s, we only have arrow up because there's only 1 electron in that orbital. In order to show me an orbital diagram, you have to write the electron configuration above the orbital diagram so that they coincide. If you just draw a box with the arrows up and down, I don't know what principal energy level you're referring to. So that's why we have to do it like that. Let's take a look at another example. All right, I've chosen one that has a lot more electrons. We're going to look at nickel, and it has the atomic number of 28, so 28 protons and 28 electrons. So we go ahead and start where we were. Start at the beginning, 1s2, that takes care of 2 electrons. Go ahead and draw that 1 box down here. We know they're going to have the next one filled as well, 2s2. Then it's going to go fill 2p6. Write those out. Then after 2p6, I'm going to put electrons in 3s2. From 3s2, I'm going to go to 3p6. Now let's check numbers of electrons. So we have 6, and 6 is 12, 14, 16, 18. So I still have 10 more electrons to account for. So after 3p6, I'm going to fill the 4s2. So we'll just come down here and say 4s2. That's an S, so we draw 1 box. And we're going to go out. Then, since I have more, to 3d10. Now we don't put 10 in there because that's going to be too many electrons. Let's go back and check our numbers. So we have 6 and 6 is 12, 14, 16, 18, 20. I can fit 10 in the d orbital, but I only need 8 because 28 is all I need to account for. So I'm going to say 3d8. For the d orbital, remember that there are 5 different orbitals or rooms for the electrons to go in. So we make sure that we have 1, 2, 3, 4, 5 in this level. So let's go back up and let's look at our orbital diagram, how it would look. Full house all the way down. So we're just going to fill this in like this. Whoops. Should look like a half arrow. So half the arrow. So I'm going to make sure that they have opposite spins. Go ahead and fill these in. Not getting much better there. Okay. Now, this 3D does not have a full house. So you do this like you would if you were going to put people up in rooms. You have 5 bedrooms and you have 8 people. So ideally, each person, or each electron in this case, would have its own bedroom. Remember, electrons repel each other, so they really don't want to share orbitals to begin with. And if they do, they have to have opposite spins. So we put each one of them in a room to themselves. So that accounts for 1, 2, 3, 4, 5 of the 8. And then we go ahead and we go back and we double them up from that point. So we have a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons. And these two are put in separate rooms or separate orbitals because that's as far away as they can get from each other and it's the most comfortable for the element. So this is what an electron configuration written longhand and your orbital diagram would look like for nickel. You're just going to have a few of these to practice. Make sure that you follow this chart for today, and tomorrow we'll be on to something else. And that something else will be easier and hopefully be able to connect some dots to the periodic table so you'll be able to understand it. So for right now, just follow the pattern and follow the instructions.